In this video, we'll discuss how we extract pure aluminium from aluminium ore. The most common aluminium ore is bauxite. Bauxite is chemically Al2O3.2H2O. Bauxite in nature is found mixed up with a bunch of other oxides, like oxides of iron, silicon, titanium, all mixed together with bauxite. We want to get rid of these oxides because these are impurities. Now, in metallurgy, impurities are given a technical term called gangue. We want to get rid of all this gangue while we parallelly extract out pure aluminium from bauxite, right? Let's figure out how this works. So this entire process is divided into two processes, Bayer's process and Hall's process. Bayer's process takes bauxite and gives us aluminium oxide. This is also called alumina. And Hall's process extracts out pure aluminium from alumina. Remember I talked about gangue, the impurities? These will be eliminated in Bayer's process. Okay, let's go and discuss Bayer's process now. Just as a side note, just before we begin the chemical Bayer's process, we have some physical preparation to do, and that's done by crushing the ore in a ball mill. This is how a ball mill looks like. Let me pause. So we have hard balls mixed with our reactant, and what we do is, this is just a physical preparation. We take our bauxite and all the impurities, put it into the ball mill and crush it in this ball mill. These hard balls crush our ore, right? And that helps in the chemical reaction. Once we're done with this, we move to the chemical process. Okay, so this entire Bayer's process does not happen in a single step. There are 3 steps to Bayer's process. It may look a little complicated, but I'll explain everything in detail. It's pretty simple actually. So we start off with bauxite. We wash it in NaOH, and that gives us NaAlO2 along with water. Now, this entire process happens at a very high pressure along with a high temperature of 150 degrees Celsius. Just as a side note, sometimes we also use Na2CO3 in this reaction. The reaction is similar. We just get some carbon dioxide as well as the product. Let's not worry about it too much. Just want to let you know that sometimes instead of NaOH, Na2CO3 is also used. Okay, remember I was talking about gangue? Let's see how some gangue is removed in this step. So these are the products, right? Our products, NaAlO2. There you go, right? What happens is, at the end of this reaction, we see that we have some kind of red precipitate at the base of our reaction tank. This red precipitate is called red mud, and it actually is Fe2O3 and TiO2. Two of the oxides that we wanted to get rid of get precipitated in this step. Though we're still left with SiO2 dissolved in the solution, we're done with getting rid of 2 of these impurities, right? Okay, now let's look at the next step. In the next step, we want to take NaAlO2 and get AlOH thrice, right? Let's see how that goes. So here we have our NaAlO2. We heat it up with water, not very hot, just 50 degrees C, and we end up getting NaOH along with AlOH thrice, which comes down as a precipitate. Let me show you how this looks. So this is our aqueous NaOH, right? This is our AlOH thrice. Okay, let me mark that. There you go. It's interesting that SiO2 in this step stays dissolved in the solution, whereas AlOH thrice, what we need is precipitated. So this time we take the precipitate and discard the solution. So we take AlOH thrice and we've discarded the solution. Now we heat this AlOH thrice to a very high temperature of 1000 degrees C. That gives us Al2O3 along with water. So these were the 3 steps of how we got from bauxite to alumina. Okay, now let's move on to the second part of our process. That's Hall's process. This is a very interesting process. So it's very simple and straightforward and beautiful. So we've got alumina, right? We take a steel tank and we put our alumina into the steel tank. And this is what we have now. Now, if we were able to separate aluminium and oxygen, we'd get aluminium, right? And that's our final aim, isn't it? So what if I was able to separate this ionic solid Al2O3 into its constituent ions? That would help us, isn't it? And for that, we need to melt Al2O3. So how do we melt it? What we do is, along with alumina, we add cryolite and fluorspar. sounds like weird names, but let me explain what they are. So cryolite is Na3Al(F6), fluorspar is CaF2. These two chemicals, when they are added with alumina, reduce the melting point of alumina. So it's easier to liquefy alumina now. And the difference is drastic. Normally, alumina has a melting point of 2000 degrees C. But when we add these chemicals, it reduces the melting point to 1000 degrees C. That's a huge gain, right? So we can save on a lot of energy. Now, when alumina is melted, we are going to get our aluminium ions and oxygen ions. Now, all we've got to do is add electrons to our aluminium ions, and then we'll get aluminium metal, right? How do we do that? We take a battery, right? And what we're going to do is, to the negative terminal, we connect what we have as a lining of the tank, right? We line the tank with this graphite material, and that forms our cathode. Right. To the positive terminal, we connect our anodes, which are also made of graphite. Great. Now, don't you think our Al3 plus ions would want to rush towards the negative terminal or the negative electrode? Right? That's exactly what happens. Al3 plus goes towards the negative electrode, while O2 minus goes towards the positive electrode. Great. What is happening at the cathode? Can you guess? Yes, electrons are going to flow out of the battery and they are going to come towards the cathode, right? And at the cathode, Al3 plus 3 electrons is going to give us aluminium, pure aluminium metal in liquid form, right? And that aluminium metal, since it's more dense, is going to settle at the base of the tank, and we can, extract it out using some kind of, hole output pipe here, right? And that will give us molten aluminium, pure molten aluminium, right? And that's what we were looking for all this while. Okay, so we've gotten what we need, but we still need to complete the entire reaction. We need to see what's happening at the anode. So at the anode, O2 minus is going to give us oxygen gas along with 4 electrons. So the oxygen gas starts getting released at the anode, and these electrons want to flow back towards the positive terminal, right? Because they're attracted to the positive terminal. So that sums up Hall's process. Okay, I just want to add one more thing before we move on. At the cathode, we have a reduction reaction. At the anode, we have an oxidation reaction. So this redox pair is what gives us molten aluminium. Okay, let's summarize. This entire story had two parts, Bayer's process and Hall's process. The first process, Bayer's process, took us from bauxite to aluminium oxide, also called alumina. This process had sub-parts, sub-steps, right? The first step gave us NaAlO2. It was during this step that we got rid of Fe2O3 and TiO2, right? The gang. In the next step, we got AlOH thrice, right? And during this process, we got rid of SiO2, right? And then the last part of this process gave us alumina. So that was Bayer's process. Summarizing Hall's process, we got some batteries and a bunch of stuff, and we were able to extract out pure molten liquid aluminium from alumina, right? Now, I just want to show you one thing before we close. This first part, Bayer's process, is a chemical process, right? Whereas the second part, Hall's process, is an electrochemical process. That's it for this video. If you'd like to take a screenshot, go ahead and do so. This slide has pretty much all the information you need to understand the chemical processes involved in the extraction of aluminium. That's it for this video. Thanks for watching.